I'm hoping my clicker is going to work for me. So maybe. Yay. We're starting a new unit. Our unit's going to be about chemical reactions. I hope you find it's going to be a fun unit because I always look forward to this unit. We're going to do lots of fun reactions. But we needed to start with some basics. So, like definition-wise, chemical reactions are what occur in lab and life. So yes, that's the blank. You might want to fill that in. So eventually we're going to go into lab one day and we're going to have like major big lab day with lots of chemical reactions. Those are what we do in lab. So you're going to be manipulating chemicals and test tubes. That is chemical reactions. What we write on our paper for chemical reactions are chemical equations. So chemical equations is what is actually written down. We don't technically write down a chemical reaction, even though we often say that. I don't mind if you say that. But in a vocabulary perspective, it is when you write it down, it's a chemical equation, not a chemical reaction. So just want to let you know. Okay, so next up we have a word equation. That's one way to write it down on paper. I know this is going to be so confusing. A word equation shows the reaction with words. I know. Try to figure that out, right? Yeah, so word equation is where we write out all the words for the reaction. So I'm like watching a reaction happen in lab. On my paper, I'm writing out in words what's going on. So an example of a word equation would be like this. Sodium iodide and lead 2 nitrate yield sodium nitrate and lead 2 iodide. Now I hope you'll see I already wrote that down on your paper for you, so you don't have to try to copy all that down super fast. You're welcome. Okay. But that's a word. Notice how it's all words. That's a word equation. It is the definition. It is not something we do often, but it is something that you should be able to handle. We will be practicing that a little bit throughout this unit. The next kind of equation is a skeleton equation. A skeleton equation is where you show the reaction with symbols. I would most definitely expect you to be able to write this for a reaction, where instead of writing out all those words, you're going to write it out in symbols. Now, that does not mean that this is going to be quick to do. We're going to be using all the chemistry we've learned so far in doing this, but it is an expectation that you will be able to, upon seeing a reaction, write a skeleton equation. So we're going to take that word equation we just had, and we're going to write a skeleton equation for it. So here's my word equation again. I'm going to turn these words into symbols. So the symbol for sodium is Na. Now you might not want to write this yet. You might just want to pause a moment and watch how we do this. Okay, the symbol for sodium is Na, but more than that, Na is in group 1A. So it's Na plus 1. Now iodide, and again, you may not want to write this yet. You may want to wait till I get to my final conclusion, because there's a couple steps going to go on here. But iodide symbol is I, and it's in group 7A, so it's a -1. And then check this out, I have the word and in a skeleton equation, that becomes a plus sign. Even though we don't actually add chemicals together, it is the symbol we've picked to show that this is a different chemical than this. They're not combined together. They're not bonded together. They're separate. Lead symbol, anyone know lead symbol? It's a little weird. It is Pb for plum bum. It's Latin name. With the Roman numeral 2, guess its charge? +2. So I got Pb +2, and then nitrate. Who remembers nitrate? Well, that's just fine. I haven't asked you to know it. What was your guess? Okay, there is an N in it. Nitrate's one of those polyatomic ions that's on the pink sheet. So there you go. So I don't expect you to have it memorized. I would expect when I hand you a pink sheet, you could find nitrate and you look it up, and from the pink sheet, it'd say NO3 minus. It's a -1. Okay. Now I have the word yield, and the word yield means it's arrow time. As we show, here's all these chemicals, and they're going to now form all these chemicals. So we got like a right side and a left side going on. And you can see I've given you some plus signs and some arrows. So in a minute, when we get our final results, you'll be able to put that there. Sodium is still Na, still a +1. Nitrate is still on the pink sheet, still an NO3. Lead is still lead, it's still a 2. And the word and is again my plus sign, and then I have iodine again as a -1. Now here's where we're going to get what you actually want to write down on your notes page. All I've done is just figured out the symbols. I haven't actually put the compounds together. We got to do that. Remember the method we use to put our ions together into a compound? It starts with 2 C's. Not enough of a hint. I know you're stuck since then. We're going to do the crisscross method to make our compounds. So what happens when I crisscross a 1 with a 1? Do we write ones? So does it change anything? No. So I get NaI. So that would be something you'd want to write in that first blank. It's that NaI. That is my final compound there. And then you can see I'm going to have the plus sign. Nope, I went too fast. Okay, so I'm going to crisscross Pb2 and NO3. So how many NO3s is that going to end up with when I crisscross? 2, because the Pb is a 2. So when I put a polyatomic ion down with more than 1, I'm going to use parentheses there. So the 2 goes to be with the NO3, which I put in parentheses. And the 1 from the NO3 goes with the Pb. And that's what you'd want in that blank after the first plus sign. And I have my arrow. And I'm going to crisscross Na and NO3. And that should be pretty easy because they're both 1. So what do I get? Do the ones change anything? No. So I get NaNO3. Notice I'm not writing the ones. We don't write the ones. And then I have way over here on the far right, I have a Pb +2 and I -1, and I'm going to crisscross. So how many Pb's will I end up with thanks to the I? How many Pb's will I end up with thanks to the I? 1. How many I's will I end up with thanks to the Pb? 2. And so it becomes PbI2. And I hope you see how this zeroes out the compound. Pb is a +2, so it's going to take 2 of these -1 I's to zero it out. That's exactly what crisscross does for us. It tells us how many it's going to take to zero out the compound. Okay, so this, which I hope you've written down, what I have here in white, this is our skeleton equation. So when you don't have anything written down and you're going to write a skeleton equation, you got to keep in mind, hey, what's the symbols, what's the charge, and I got to crisscross. All right. So that is, I'm hoping, again, that's what you have in your blanks, so that's our end result. There we go. Our final type of equation is a balanced chemical equation. And a balanced chemical equation shows that we have the same amount of each element in both the reactants and products. And most definitely all unit long and for the rest of the semester, anytime you're using an equation, you're going to have to get it to a balanced chemical equation state. We have to do chemistry with balanced chemical equations to be doing correct work. Now, I don't think I left quite enough space on my third compactor, but I was going to balance this here. And balancing is very, very, very much just accounting for all the atoms, making sure there's the same amount on both sides of the arrow. On the left side, the reactant side, I want the same amount of Na as I have on the product side. And this is a guess and check method. You're going to guess what makes it balance. You're going to check if it works. If you guess wrong, you erase it and you check something else. I have the advantage I'm working with markers, so I can erase pretty easily. But all I do is I just start checking and see what happens. So tell me this, how many NAs do I have on the left and the reactant side? 1 Na. And how many do I have on the product side on the right? 1. Okay, that balances so far. That's okay. How many I's do I have on the left and the reactant side? 1. How many I's do I have on the left and the product side? 2. Okay, that does not balance. I have 1 over on the reactants. I've got 2 on the products. So I'm going to add a 2 in front of NaI to give me 2 I's on the left. Notice I'm changing the coefficient. I can't change the subscripts. That comes from the crisscross. Can't change those after crisscrossing. But I'm going to have 2 groups of NaI to give me 2 I's. Now, did you notice what that just changed? The Na. Now I have 2 NAs on the left, so what am I going to have on the right? I'm going to need to put a 2 there to have 2 NAs. Now, I also see on the right, when I put the 2 in front of the NaNO3, that gives me 2 NAs. How many N's does that give me? How many nitrogens? 2 on, now I'm on the right side, so 2 on the right. How many do I have here on the left in the reactants? 2. Oh, that does match up. So I'm probably on the right track. Going back to the product side on the right, I put a 2 in front of NaNO3. How many O's does that give me? How many oxygens? 6. Over on the left, what do I have? 6. So I'm looking good so far. Only one element I haven't checked yet, and that's the PB, the lead. So how many PBs on the left? How many on the right? That it's balanced. Everything matches. That will be your job to figure out what numbers go in front, what coefficients go in front of these to make it balanced. Okay. So there's my end result. I needed to have 2 groups of Na and 2 groups of NaNO3 in order to balance the whole thing out. That is going to be an expectation is I can give you an equation and you can bring it to a balanced chemical equation. All right. Now the reason we balance is because we have to obey the law of conservation of mass. Okay. Well, I already said that. Thank you. So the law of conservation of mass says, I hope this rings a bell from earlier science classes, like years ago, earlier science classes. I know you've slept since then. Law of conservation of mass says the mass of the reactants is the same as the mass of the products. Mass of the reactants is the same as the mass of the products. Now, mathematically, what am I saying when I say the same? Equals. So we can totally, and we're about to prove it, we can say the mass of the reactants equals the mass of the products. So we're going to prove it with this one. Find your periodic table in your calculator. Got so many papers around here. Okay, say the name again. Oh, yeah, Ahmed, yeah. Okay. We're going to prove the law of conservation of mass. So we need masses. Where do we always go for masses? Periodic table. Okay. Let's start here. You got calculator, you got periodic table. I help out. For today, let's just round to the whole number. So what is the mass of Na? 23. Add that to I, which we're going to call 127. So add that up. And then what should you do to it? Multiply it by 2. Yes, because there is that 2 in front of the NaI. So 1 Na, 23, plus 1 I, 127, times 2. And I need to get a marker here so I can write this down once you tell me what it is. Okay, so 2 times NaI, what do we get? 300 grams per mole. Okay. Now let's do that to PbNO32. Ooh, that's something that's going to take a bit more work in the calculator. Good thing I allow you to use a calculator. Pb, let's round that. Let's call it 207. And let's call that 14. Oh, let's call that 16. And be careful here. You need 1 Pb added to 2 N's added to 6 O's. Make that all happen. I don't know how proportion. One Pb added to 2 N's added to 3 O's. Somewhere around to 300, I'm going to guess. What do we see? Not, okay, not yet. Okay, I'm hearing it too. I get a 283 over here. Is anyone else getting that? 331 over here, 331, 330, okay. I'm going to go with 331. Hopefully the group consensus is correct. We'll find out. Now over on the right side, I have to add up an Na, which we're going to call 23, an N, which we're going to call 14, 3 O's, which we're going to call 16. And then once I add all that up, I still need to multiply that by 2. 170. Okay, I'm going to go to group consensus. We will find out in a minute if we're right or not. And then I need a Pb and I2. So 1 Pb, which we're calling 207, and 2 I's, which is 127 each. So what's that, like a 500 something? 461. Okay. Group consensus is 461. Now the moment of truth. What did I just say the products and reactants should do? Equal. So, well, this side's easy. that looks like 631 grams per mole on the reactive side, on the left side. Not so easy over here, so help me out. 170 plus 461, do we get? Yes. We do. 631 grams per mole. All right. So thank you for helping me do that. That is something I would expect you to be able to do. Now, additionally, what I'd expect you to be able to do is if I gave you, in the step where we had the 4 compound individual masses, if I gave you 3 of the 4 and left a blank, I'd expect you to be able to fill in the blank. So whichever side you have complete data for, you would total and you subtract the others. Okay, just a simple solve for an X kind of thing. So yes, law of conservation of mass says the mass of the reactants is the same as the mass of the products, and we definitely see that is true. And again, I would not be off on my expectations to what if I gave you the 300, the 331, the 170, and a blank for the last one. Could you fill in that blank? I hope you'd say, yeah, I would total what's on the left in the reactants, and then I would subtract the 170 from it, and what's left over, it's got to go in the blank. It should be that easy to fill in a missing blank, or I could just ask you to just add it all up like I just did. We could do that too. Okay, other symbols that you will find in chemical equations. Some of these are oh so shocking, I know. Guess what an S in parentheses might stand for? Solid. And an L in parentheses would stand for liquid. G is gas. I mean, if you have blanks, fill them in. But those, like, even if I didn't mention it, students get those. And then there's one weird one. Because most students don't know Latin. I'm just curious, do you know Latin? Okay, and I wish my high schools had even offered Latin. It would have been helpful. A lot of chemistry is actually written in Latin. Okay, but oh yeah, choir uses a lot of Latin too, no doubt. AQ in parentheses is short for the Latin word aqueous, which means dissolved. And a lot of other languages that are Latin based have words for water very similar to aqua. So yeah, we've got aqua, we've got agua in Spanish. Lots of Latin-based languages use a word similar to aqua. So aqueous means it's dissolved. So you might want to write that down if you see it. Here's what I'm going to do. I want to use these symbols, and so I picked a word equation that I put all these symbols into so you can see how it's going to look when you do these. So I'm going to make you seem like this is super easy. It is super easy for me because I've practiced. With practice, you'll get to the point where you can do this. But I'm going to turn this word equation eventually into a balanced chemical reaction. So you can see I start out with solid sodium bicarbonate. I know sodium is Na. I know bicarbonate from the pink sheet is CO3. I know each one is a 1 and a 1. Sodium's a +1, bicarbonate's a -1. And I know it's a solid, so notice the new thing I'm adding to this one is a little S there. And I left you a space, just an empty space on your notes page where you can hopefully be writing this in as I go. And then we have aqueous hydrogen acetate. Well, hydrogen is H, it's a +1. Acetate is C2H3O2, and it's a -1, and that's right off the pink sheet. Don't expect to know that, you just look for it on the pink sheet. Here are both 1s, so my crisscrossing is done. And it is aqueous, so I'm going to write that little AQ in parentheses because it told me aqueous in the equation. I'm going to put that there. So over here, I now have aqueous sodium acetate. Well, sodium is Na. Acetate is still C2H3O2. I found that on the formula chart. Sodium is still a 1, acetate is still a -1. So my crisscross leaves it the way it is. It told me it's aqueous, so now I have that little AQ to say it's aqueous. And then the super easy parts, liquid water. What's water's formula? H2O, right? It's liquid water, so what do I put in the parentheses? An L, liquid water. And I get carbon dioxide gas. Well, carbon dioxide is CO2, 2 oxygens, dioxide, and it's a gas, and boom, there we go. Okay. So that is how it would look to use those symbols we just talked about. Hope you took a moment to write that into the big space I left you on your notes. Okay. I'm about to balance it. And I'm going to balance it using 2 clever tricks. I want to share these tricks with you in case you want to use them. So for you to see the clever tricks I'm about to use, I color-coded parts. So notice I took the elements and I color-coded them similar so you can see where they are on the left, where they are on the right. Here's what I'm going to start with. I'm just going to start with the Na. So how many sodiums here on the left? 1. How many on the right? 1. Okay. Now I'm going to go to the H. Look at the blue H's. Mr. Cohen. Okay. Can I send them in like half an hour? Okay, I'll do that. Okay. Notice I have on the left 2 blue H's. When I see an element and more than 1 compound on the same side, I like to leave it till the end. So I'm going to skip my H. Let's look at the C. How many C's do I have on the left? How many do I have on the right? 1 and 1. So far, so good. Look at my O's on the left and look at where they are on the right. Oh, there are more than 1 compound. I'm going to save that till the end. Look at what I did with the C2H3O2. I colored it all the same. Did C2H3O2 change from left side to right side? No, it did not change from left side to right side. So guess what? I can keep it together as one thing. So 1 brown group on the left. How many brown groups on the right? 1. It's balanced. Now let's go back to the few elements I get into. How many blue H's on the left? 2. How many blue H's on the right? 2. How many purple, that's supposed to be purple, how many purple oxygens on the left? And when you add them, how many purple oxygens on the right? 3. So my 2 little tricks are, I noticed I have a big group that didn't change. So I just considered it as a group. I did not want to break it apart into C's and H's and O's. I could have, but I didn't want to. Notice my other little trick. Hydrogen was in more than 1 place. I saved that towards the end. Oxygen was in more than 1 place. I saved that towards the end. So did I have to add any numbers to balance this out? No, I didn't. It's already balanced, and sometimes that happens. It could be that way. So there we go. So our skeleton equation turned out to also be our balanced chemical equation. It can happen, but you don't figure that out until you check. All right. Let's move on to finishing up some thoughts here. Okay. I know this is still shocking. I'm saying so much that is shocking in one morning. During a chemical reaction, there's a chemical change. And that's what you're supposed to put in the blank here. So what tells me a chemical reaction occurred? I would notice there is a chemical change. Not surprising at all how we say that. So just to review, because it's been since the beginning of the year, the opposite is a physical change. So don't think too hard about this. The background I have there is an ice cream melting. Is the ice cream changing? Yeah, it's going from solid to liquid. Okay, but that is just a physical change. And if you don't know why, that's okay. We're about to explore this idea of physical chemical changes very thoroughly. So you can be very careful to identify, yes, this is a chemical reaction because I see a chemical change, or no, it's just a physical change, it's not a chemical reaction. So during a chemical change, I almost said the wrong word. During a chemical change, here's how you know it's a chemical change. Bonds are broken or formed or both. During a chemical change, bonds are broken. The atoms come apart. Or bonds are formed. The atoms join together. Or both. Some things are broken apart and some things are put together. We can have both happen, or just one or the other. And of course, I have a cool little graphic of different chemical changes going on. We're going to explore this pretty thoroughly, making a contrast between chemical changes and physical changes, so you're not going to be confused. Especially when we get to our big lab and I start asking you questions of, is this chemical change, is this physical change, and you're staring at it happening in lab, you will know what you need to look for to figure it out. Okay, so my first example, I have glass. I have yellow paint, and I paint the glass yellow. My question to you is this a chemical change? Give me a thumbs up or down. What do you think? Chemical change. A lot of people saying, no, not a chemical change. Well, you are correct. So the little blank there is a no. It is not a chemical change. Okay. Why is it not a chemical change? That's a little bit harder question. I mean, obviously you could be like, well, if it's not a chemical change, it's a physical change. That's not what I'm asking for. Why is it not a chemical change? The glass is still glass. The paint is still paint. I'm just putting them closer together because I'm painting the glass. That's why it's not a chemical change. I'm just putting them closer. That's all I'm doing. The glass does not change. The paint does not change. Putting them together. Closer. So if I were then to take a razor blade and start scraping the paint off the glass, what kind of change would that be? Still physical, because now I'm just separating them. The glass is still glass, the paint is still paint. I'm just separating. So this is not a chemical change because we're just putting the glass and the paint closer. That's all we're doing. We're not changing the bonding. Now on the back, I have a picture that's going to be very similar looking. Notice I started here with transparent glass and some paint, and now it's not transparent, it's yellow glass. On the back, I have two beakers that are transparent. And when I pour one beaker into the other, this is what happens. It's yellow, just like the painted glass. Do you think this is a chemical change? Okay, you kind of got an idea. Yeah, this is a chemical change. I had transparent liquid. Now there's a yellow floating around it, which, by the way, is a solid. Oop. I had another slide there. I guess not. Oh, I better put on your papers. I drew arrows to point out what's even. It's on your paper. I drew arrows to point out what the yellow solid is. Now, for it to be a chemical change, what has to happen? Bonds broken or formed or both. So I rewrote the chemical equation. Let's look for bonds broken. For my NAI to end up in separate spots, what do I have to do to the bond between them? Break it. For the PB and NO3 to end up in separate spots, what do I have to do to make that happen? Break the bond. For the Na and the NO3 to come together, how do they stick together? They form a bond. For the PB and the two I's to come together, what are they doing? Forming a bond. So this is a chemical change because I am breaking bonds and forming bonds. It is a chemical change. This is a chemical reaction. So you do already kind of have this idea from just experiencing life that this is not what I would have expected from just a physical change. I bet it's a chemical change. Here's exactly why you want to call it a chemical change. We broke apart the NAI bond. We broke apart the PbNO3 bonds. We formed an NaNO3 bond. We formed PbI2 bonds. We're breaking and forming bonds, chemical change. Okay, so we're going to go through how to figure this out really well. I want this very clear. There are roughly 5 things that would clue us in to a chemical change occurring. And I have an example and a non-example for each. And then you can see I gave you blank to fill in. Now, I wrote up on the screen what's going on. You probably don't want to write that. Just write enough in those example blanks and non-example blanks for you to remember what I talked about. On the left here, I have what's a shiny gold copper bracelet, but what's happening to it over here on the side? It is oxidizing. It's got a color change going on. It's turning green. My son was oh so excited when the last Minecraft came out and there was this copper block that, given enough time, started turning green. And I was like, yay. Because this is what happens to copper. The Statue of Liberty is made out of copper. When it was first made, look at how bright and shiny. Would that not have been awesome? But I know that the designers of it would have known that eventually it would have turned green, because they knew that by then. Now, this tells me, hey, that looks like a chemical change. Can I prove that? Here's my proof. The words are my proof, but you don't necessarily need to write that down. You just might be like, my example is a copper bracelet turning green. But here's the proof. I have copper and oxygen making copper oxide. Would sound like it happened taking separate copper, separate oxygen, and then making copper oxide. Sounds like a bond formed between them, and that's exactly what happens. Now over here, like, this is probably the one time a year I ever visit McDonald's. I gotta get a Shamrock Shake. Just one, I'm good after one, but like every year, gotta get a Shamrock Shake. Well, they have milkshakes all the rest of the year. How do they make the milkshake green? Dye, green dye. So they take milkshake and green dye, and what do I end up with? A green dyed milkshake. Does that sound like bonds have been formed? No, they're just stirred together. I've just put them closer. That's all that's happened. So that, you might just put like green milkshake as down in the blank. That is a physical change. It's not a chemical change. That's a non-example for a color change. Okay. Next change, odor change. This is a fun one. So in chemistry, we have this compound called ornithine. And if you get it to lose a carbon dioxide, so do you see these two O's up here in the kind of the corner going on? Okay. And there's a carbon in the middle. If I get that carbon dioxide to leave, what I end up with is called putrescine. Guess how putrescine smells? Putrid, hence why they called it putrescine. This actually does happen naturally in decomposing bodies. That this is part of one of the many compounds that make really bad stink when, a corpse starts decomposing. Listen to the way I put this in words. Now, again, I don't know that you necessarily need to write down the words. I just want you to hear the way it sounds. Ornithine yields carbon dioxide and putrescine. For one thing, ornithine, to make two things, carbon dioxide and putrescine, what's that sound like happened? A bond broke. And you can actually see in the way that they're drawn, it is this little stick bond right there that actually does break. Okay. Over here, I bet if I asked, several of you could pull out perfume or cologne, right? You put it on your skin. So perfume and skin, does that form a bond? No, you're just putting them closer together. Makes perfume skin. So it's not a chemical change. It's just a physical change to put them closer together. Okay. Now, does that mean your skin doesn't smell? No, your skin does now smell. That's why we like perfumes and colognes and stuff like that. But it's not bonding to your skin. It's just touching. Temperature change. You got to be careful with this. You got to think about it well. So over here, I have, that was two solids mixed together, and they froze to a wood block to where now you can pick up the wood block with the container. Does that sound like a chemical change? Well, okay, if I put in words, can we prove it's a chemical change? So here it is in words. Barium hydroxide and ammonium chloride yield barium chloride and ammonium hydroxide. For them to switch parts, would I have to break and form bonds? Yes. Now, I don't know that you need to write down the words again. You might just write down, like, using two chemicals to freeze a wood block to a flask or something like that. I used to actually do this all the time with just ice and salt in the dorm cafeteria. Because then after I froze my glass to the tray, I could just pick up the whole tray by my glass and take it to the conveyor belt I took in the kitchen. This is yummy, yummy, cooking some pasta. Do any of the bonds change when I cook pasta? Right, so hard pasta becomes soft pasta and warm. It becomes warm. Not bonding anything, I'm just warming it and softening it. So no bonding occurs here. A lot of cooking, if all you're doing is heating it up or cooling it down, that's just physical changes. That's not a chemical change. Okay, next up, formation of a solid. Have you ever seen yeah, you can just leave it there. Have you ever seen a really, really old faucet have all this crud on the faucet? We're actually like way down there. Okay. We call it hard water deposits. So you might just put down in the blank hard water deposits. Is it like the water's just evaporating, or is there actually a chemical reaction occurring? Well, here's my proof in words. Calcium chloride and sodium carbonate yield calcium carbonate and sodium chloride. You see how they switched parts? To switch parts when I have to break a bond and then reform a bond elsewhere. Yeah. Okay, so hard water deposits does definitely have a chemical change. This is Lake Michigan in the wintertime. Well, guess what all this blue pointy stuff is? Ice. Okay, so can we freeze liquid water to ice? Yeah, we can. Did I break any bonds in doing that? No, actually, there's only one ingredient, water. And it starts as water and it ends as water. So most definitely no bond breaking or forming here. So ice forming is not a chemical change, just a physical change. Hard water deposits are a chemical change because there is some bonds breaking and forming. Okay. Formation of a gas. On the left here, I have what's often called elephant's toothpaste. Because I don't know if you've ever used one of those toothpaste where it has the stripe in it. It's obviously like, it looks like that, but for something giant like an elephant. Not that elephants actually use toothpaste. How does this work? Well, if you don't know, I'm going to tell you. It's hydrogen peroxide yielding water and oxygen. How many things do we start with? Just one. How many things do we end with? Two. Guess what has to happen to turn one thing into two things? Breaking a bond. Okay. Here I have a balloon being filled up with some helium. Are any bonds forming? I mean, the balloon changes. It looks like I'm forming a gas. Am I really forming a gas? Where was the gas before I put in the balloon? In the tank. And then where's it after? In the balloon. So I'm just moving the gas from in the tank to in the balloon. That's all I'm doing. So not a chemical change, because it's still the balloon. It's still the helium gas. I'm just putting the two together. And, well, click too fast. The final one, production of light. This is always a fun one. So glow sticks. Don't we all just love glow sticks? If I had to ask you, even without showing any proof there, is glow sticks a chemical reaction, what would you say? Yeah, because in fact, what you have to do to get the reaction started, you snap it because there's a glass vial separating the ingredients, and you have to break into that glass vial. And then when you break into that glass vial, it gets to mix. Okay. If you want proof, here's the proof. We take an oxalate ester and peroxide. It's probably the peroxide that's in the glass vial, and it turns into dioxazethane dioxazethane, something like that. Does that sound like bonds have been changed to turn that and that into that? Yeah. I like an old light bulb. What do I need to do to turn on a light bulb? Yeah, put electricity into it. How does that actually work? Well, the electricity literally heats up the wire until it glows. And that's what gives you light. So the wire getting hot. Hot. Does that sound like a chemical change? No, it's still wire. In fact, most light bulbs are filled with argon to prevent a chemical reaction from happening. Because if a chemical reaction happened, the wire would like burn up or disintegrate and you'd have to replace it. So filling them with argon gas actually helps them last longer. So notice how you can kind of clue into the idea of, are bonds broken or formed? If so, it's a chemical reaction. If bonds are broken or formed, we tend to get a new product or new products. We get something new out of it. When my wire heats up, is it no longer a metal wire? Stays the same. It's a metal wire. It's just hot. Okay, so that's it for how we can tell chemical reactions. Your assignment over the weekend is going to be to balance some chemical equations. So I actually hope you find that this is rather simple and easy, because that is the actual goal. Just practice balancing some chemical equations. If you don't find it simple and easy, then you just want to keep working at it until you see how to do it. This is worth working through.